So in the previous slide, we developed these two different ideas of pi donor ligands that have ligand group orbitals that are lower than the metals, and we developed the idea of pi acceptors that have ligand group orbitals that are higher in energy than the metals. So here's a figure from your textbook that shows us kind of the relative effects of pi acceptor and pi donor ligands. So like we said before, in the case of the pi acceptor ligands, those are increasing delta. And what's happening there is that we imagine the metal is pi bonding with, say, for example, the pi star orbital on carbon monoxide, carbonyl ligand, okay, which would look something kind of like this. And in this way, the metal is actually donating electron density to the ligand. Whereas in the pi donor case, we're imagining the metal is overlapping with, say, an unhybridized p orbital on, say, a chloride ligand. So once again, these T2G orbitals have the right symmetry to overlap with a pi orbital. And so this would be this is like a lone pair, a filled orbital on chlorine, and we imagine that the chlorine is donating extra electron density to the metal. Okay, so pi acceptor ligands, the reason that they use their empty group orbitals to bond is that they're closer in energy to the T2G metal orbitals, and pi donors, just because of their identity, because of what atoms are involved, they use filled T2G orbitals to bond to the metal. So it turns out it is actually this pi donor acceptor property that leads to the spectrochemical series. So these ligands that cause really large separations in delta, these are pi acceptor ligands. Like CO and CN, they have unfilled orbitals that can accept electron density. And the really small delta ligands, these are pi donors. And so you see they have extra lone pairs to be able to donate to the metal. And then these things that are in between, so like ammonia doesn't have low-lying pi star orbitals, and it doesn't have extra lone pairs. It just has the one lone pair that it uses to sigma bond. So nitrogen ligands, they tend to be sigma bonding only. And so we see that the continuum of the spectrochemical series is the continuum between pi acceptor and pi donor ligands, and we pass through neither pi accepting nor pi donating, sigma only, in the middle. So some typical examples of complexes that might fit these different groups would be, for example, something like hexacyanochromate would be an example of a metal complex that has all pi acceptor ligands. And this complex is, for example, it's a very light yellow because it absorbs in the close to the UV range, because there's a big difference between the T2G and the EG orbitals. For the sigma bonding only, a complex that might represent that would be something like hexaamine chromium 3 with ammonia ligands. So ammonia can't really do pi bonding either way. This compound is purple, or violet, we said. Purple because it absorbs yellow. Okay, we said this first one absorbs purple. And then finally, an example of something with pi donor ligands might be something like CRF6, which we said was green or blue because it absorbs red or orange. So we see that if we look at the color that it's absorbing, so purple, that's the biggest energy, then yellow, that's a medium energy, that's smaller, and then red-orange, that's the smallest. So we can see that as we change the ligands, we can change the size of delta based on, sort of consistent with these pi donor, pi acceptor properties.